Hello everyone, welcome back to the channel. I am Dr. Vikrant Yadav, Assistant Professor in Department of Mathematics, School of CS and AI at SR University, Warangal. In today's video, we are going to discuss an important and very powerful numerical method, Newton's forward interpolation formula. Now, before we begin, let me ask you a simple question. What do you do when we have some data points, but we need to estimate a value that is not directly given? For example, suppose you know the values of a function at certain points, okay, but you want to find the value at a point in between. What should we do? This is exactly where interpolation comes into picture. And among different interpolation techniques, Newton's forward interpolation formula is one of the most efficient methods, especially when the data points are equally spaced and we are in estimating values near the beginning of the data set. So in this video, we are going to understand what is interpolation, why it is needed, okay, the concept of forward differences and the idea behind Newton's forward formula, and how we use it step by step in practical problems. Okay, so don't worry if this sounds new to you. I'll explain everything in a very simple and intuitive way, just like we do in a classroom. And by the end of this video, you will not only understand the formula, but also feel confident enough to apply it in numerical problems. So, if you are a student of engineering, mathematics, data science, or any field involving numerical computation, this topic is extremely useful to you. So let's get started with Newton's forward interpolation formula. In this slide, we are introducing the concept of interpolation. First, let us understand the definition. Interpolation is the process of estimating the value of a function at a point within a known set of tabular data points. Okay, this means that we already have some known values of a function and we are trying to find the value of a value at a point that lies in between those known values. Now, mathematically, we assume that we are given n plus 1 points, okay, which are written as x naught in pairs actually, x naught y naught, x1 y1 till xn yn. These are a total of n plus 1 data points. Here, each xi means these values x0, x1 till xn represents an input. Each yi represents the corresponding output value. Okay, so basically these are known data points of a function. The main goal of interpolation is to estimate the value of y for some value of x that lies between x0 to xn. So we are not going outside the given data, we are only working within the range of known values. Okay, so then now an important assumption in this slide is equal intervals. Equal intervals means that the step size h, this step size h between consecutive x values, okay, between any two values of means any two xi values is constant, which means h equal to x1 minus x0, x2 minus x1, or xn minus 1. It should be same. So this tells us the spacing between all x values is same and the data points are uniformly distributed. This condition is very important for applying certain interpolation formulae. Okay, two Newton formulae are there for equal intervals. These are forward formula and backward formula. In forward interpolation formula, this forward interpolation formula is used when the value of x is near the beginning of the table. Okay, that table of data will be given. So this Newton's forward interpolation formula is used when the value of x is near to the beginning of the table. So if you want to estimate a value close to x naught, we will use this method. Then there is backward interpolation formula, which is used when the value of x is near the end of the table. So if the required value is closer to xn, then this method is more accurate. Okay, to summarize, interpolation helps us estimate unknown values within known data. We use n plus 1 data points. Our main goal is to find a value between given points only. When intervals are equal, step size h is constant. Okay, there are two main methods, forward and backward interpolation formulae. Okay, forward is used only when it is near beginning, and when it is near end of the table, then in that case backward formula is used. Okay, this forms the foundation of numerical interpolation techniques, which we will study in detail in the next slides. So now let us move to the next slide. So now we are going to understand the concept of forward difference operator, okay, which is denoted by the symbol delta. Symbol is delta. The forward difference operator delta is defined as delta yi equals to yi plus 1 minus yi. This means we take the difference between two consecutive values of y, okay, and specifically we subtract the current value from the next value. So in simple terms, forward difference equals to next value minus current value, which is written as delta yi. Okay. Also, we can extend this idea further. The second order forward difference is defined as delta square yi, that is given as delta yi plus 1 minus delta yi, and this. Similarly, the third order difference is given by delta cube yi equals to delta square yi plus 1 minus delta square yi. Okay, so basically this process continues like that only. Now we have first difference, difference of original values. Second difference, that is differences of first differences. Third differences, differences of second differences. Okay, now let us understand this concept with an example. We are given the table, okay, in which this is the input value, that is x. This is the function y equal to x cube. This is the delta y, this is delta square y, this is delta cube y. Okay, so let me write it. This is x naught equal to 1, this is x1 equal to 2, this is x3 equal to 3, this is x4 equal to 4, and this is x5. No, I missed 2. So x1, x2, x3, and this is the last one is x4. Okay, by mistake I written it. So this value is actually your y naught, the value of function y equal to x cube at the point x naught. Okay, This is your y1 equal to 8. This is y2 equal to 27. This is y3 equal to 64. This is y4 equal to 120. Okay. So with this data, we are going to calculate delta y first. So the first difference, delta y means y, actually if I put here y, then yi, so it will be yi plus 1 minus yi. So your delta y1 will be equal to delta y0 actually, okay, that will be delta y1 minus y0. So here the value is this one, which is equal to 7. That is equal to 8 minus 1. Okay, that is equal to 7. Similar way, you can find out delta y1, that will be equal to y2 minus y1. Okay, so that is 27 from here, from the table, minus 8, that is 19. Okay, next value will be your delta y2, that will be y3 minus y2. Okay, that is equal to 64 minus 27. Okay, that is actually equal to 37. So similar way you can find out the next value as well, y. Okay, next value is y, delta y3. Okay, that is actually calculated as y of 4 minus y of 3. That will give you 125 minus 64, that is 61. Okay, these are the values of first differences. Now we shall try to calculate the second difference. The second difference is delta square y. Okay, that is actually equal to delta, this delta yi, actually delta square yi, that will be equal to delta yi plus 1 according to the formula. Okay, then delta yi. Okay, so let me find out delta square y0, that will be delta. Okay, so I'll be calculating this one, delta y0. So it will be delta y1 minus delta y0. So the values are 19 and 7. That should be equal to 19 minus 7. That is equal to 12 here. Similar way, you can find out delta square y1. That will be equal to delta y2 minus delta y1. So that value will be 37 minus 19. So that is equal to 18. Okay. Same way you can find out delta cube y. Okay. For that delta y cube yi, that means it will be equal to delta square yi plus 1 minus delta square yi. Okay, and these values will be attained. So the last value is actually delta cube y 0. Okay, that is delta square y 1 minus delta square y 0. Okay, that is giving you the value as 18 minus 12 from the table I'm taking. Okay, that is equal to 6. Similar way, delta cube y1 will be equal to delta square y1, sorry, y2 minus delta square by 1, and that value is 24 minus 18. That also I considered from the table, and that is equal to 6 here. Okay, so these are the final values on the table which I showed you how to calculate them. Okay, now let's move to the next slide. Now we are going to study one of the most important results in interpolation. Okay, the Newton's forward interpolation formula. The Newton's forward interpolation formula is given by yx equals to y naught plus s times delta y naught plus s minus s1 upon 2 factorial times delta square y naught plus s minus 1 s into s minus 1 into s minus 2. Okay, this term upon 3 factorial and then delta cube y naught plus and so on, where your s is given by x minus x naught upon h, where h is the step size. Okay, this is the step size. This formula helps us estimate the value of a function at a point near the beginning of the table. Okay, now let us try to understand each term in this formula. Here, yx is the value we want to find. Okay, y naught is the first value. This y naught is the first value in the table. Delta y naught, delta square y naught, and delta cube y naught. These are forward differences taken from top diagonal of the forward difference table. Okay, then we come to S, this term. S equal to x minus x naught upon h, and h equal to x1 minus x naught. Here h is the step size which is constant. Okay, and that is the intervals will be equal. And S tells us how far the required value of x is from the starting point x naught. S tells us how far the required value of x is from the starting point x naught. Okay, now let us go to the important points that you should know. Here, x naught is the first entry in the table. Okay, and S can be any real number. Then this is important because this value of x naught is important because the formula is built starting from the beginning of the table, and also this s is any real number actually. So this means x does not have to be exactly one of the given points. It can lie anywhere within the interval. X is the point at which we are going to find the value of the function y. Okay. Then differences, we use the top diagonal values of the forward difference table. Okay, that is delta y0, delta square y0, delta cube y0, and so on. These values are taken from the first row of each difference column. Okay, now again, the accuracy of this formula is best when x is close to x naught. This is very important, as if the required value is near to the beginning of the table, we use forward formula. If it is near to the end, we use backward formula. Okay. Then the formula represents a polynomial of degree n. You can see it very clearly. This yx, it represents a polynomial of degree whose degree is less than equal to n. Okay, this means it passes through all given data points, and it approximates the function using a polynomial, and that is very important point. So what this formula actually does is it builds the value of ix step by step using initial value y naught. Okay, corrections are there using first, second, and third differences, and each term improves the accuracy of the approximation. So it is really important. Okay, now we are moving to the next slide. Now we are going to solve a practical problem using Newton's forward interpolation formula. Okay, we are given a table of values for the function y equal to e raised power x. Okay, and we are asked to find the value of y at the point x equal to 1.5. Okay, also we are given that x naught, the initial value of x is 1.0, that is 1, and step size is zero point 0.5. This value h equals to 0.5. Now from the table you can see that these are the x values, this 1, 1.5, 2, 2.5. Okay, these are the values of the function, that is e raised power x. These four values under the column y equal to e raised power x. Then this is first difference, this is square difference, this is third difference. Okay, so actually you are having the values that are given in the table. The highlighted teal values, that is represent the top diagonal elements which we use in the formula, that is this value y naught, this value delta y naught, this value delta square y naught, and this last value delta cube y naught. Okay, so let us begin it. The first step is to calculate s. Okay, this s we are going to calculate, whose formula is x minus x naught upon s. X is here 1.5 given to you, h is 0.5, x naught is 1. Okay, we are putting the value, got the answer as s equal to 1. Now you are supposed to apply Newton's forward formula. Okay, the formula says, as you saw in the last slide, the formula here is y x equal to y naught plus s times delta y naught plus s into s minus 1 upon 2 factorial into delta square y naught plus s into s minus 1 into s minus 2 upon 3 factorial into delta cube y naught plus and so on. Okay, now substitute s equal to 1 in this formula. Okay, so you will see that if you put here s equal to 1, this will be cancelled, and later on all the terms will be cancelled. Okay, so the left out terms are these two only, that is y of y x equal to y naught plus delta, actually this should be delta y naught because s is 1 here. Okay, so if you put the value x equal to y equal to 1.5, so this is y naught plus delta y naught value that you need to consider from the table, and you're getting the answer as 4.4817. Okay, this is the interpolated value and it is equal to y 1.5. This is the approximate value, interpolated value. Okay, so the exact value we can verify it as well for the function e raised power x, e power 1.5 equals to 0.4817. Okay, so the result is accurate. Okay, so you can see from here that the when s equals to 1, the calculation becomes very simple. So only the first two terms contribute in this question. This shows efficiency of Newton's forward formula. Okay, so now let us move to the next example and next slide. So we are going to solve now another example where we use Newton's interpolation formula. So we are given the function as e raised power x, okay, and the value of x is the point at which we need to find the value of this function is 1.8, x equal to 1.8 basically, okay, and the value of x naught is 1.0 and h is, that is, the step size is 0.5. It is to be done using the last table only. So first step is to compute s, and your s is given by x minus x naught upon h. Okay, so here x is 1.8, x naught is 1.0, and h is 0.5. So you're getting the value of s as 1.6. Okay, top diagonal differences from x naught equal to 1.0 are y naught equals to 2.7183, delta y naught equals to 1.7634, delta square y naught is 1.1440, and delta q y naught is 0.7415. Okay, these are differences taken from the last table, the previous slide. So we are supposed to just replace these values in Newton's forward formula. Let me write the formula again here. That is equal to delta, sorry, y of x equals to y naught plus, okay. So the formula is yx equal to y naught plus s times delta y naught plus s into s minus 1 upon 2 factorial into delta square y naught plus s into s minus 1 into s minus 2 upon 3 factorial. Okay, that is delta cube y naught plus dot dot dot, that is, it will be continued like that only. Okay, now substitute s equal to 1.6 in this formula. Okay, so after substituting this value here, y 1.8 becomes 2.7183 plus 1.6 into 1.7634 plus 1.6, and this difference dash minus 1 will become 0.6, okay, upon 2 into 1 minus 1 dot 1.1440 plus this will become 1.6 into 0.6, and this will become s minus 2, okay, so it will become minus times 0.4 upon 3 factorial, that is 6 into 0.7415. Okay, so you can use the calculator to calculate all this. So after calculation, you'll find that you're getting the value of y, this value y 1.8 as 6.0413. Okay, this is the value that you're getting as 6.0413. Now, also, if you calculate the exact value, that the exact value is of the function e raised power x. If you put here in this function e raised power x as e raised power 1.8, then this value becomes 0. 6.0413. 0.0496. Okay, so this value is closer to the exact value, right? So there is small error, okay, because higher order terms are neglected here because we did not write the terms after delta cube y0 in this formula, right? So they are because of the reason that we are neglecting the higher order terms. This this error is coming. Okay, so I hope this is and you are able to understand this concept very well. Okay, so now, okay,
If you found this video helpful, don't forget to like, share, and subscribe to the channel. Thank you.